So hi everybody and welcome to this video number 15 in the solution series. So here we'll be discussing about osmosis, osmotic pressure and Van 't Hoff's relations, and then discuss three terms: isotonic, hypertonic and hypotonic. So that's the content of this video. The root word for osmosis is from Greek. So push, so osmosis comes from Greek word, so meaning push, and osmosis is the flow of solvent molecules from a region of higher concentration, that is pure solvent, to the region of lower concentration. See, most importantly, it is a flow of solvent molecules. It is not flow of solute molecules, and therefore, since it's a flow of solvent molecules, it goes from a region of higher concentration to lower concentration. See, pure solvent will have higher solvent concentration. Solution will have lower solvent concentration and little bit of solute concentration, right? So solution through a semi-permeable membrane. Now, what do you mean by semi-permeable membrane? So, semi-permeable membrane is permeable to solvents, but not to the solute particles. Okay. So, if you have a if this is your solvent, pure liquid, that is pure liquid. Then, if you have a solution, so this is your semi-permeable membrane. So, what will happen is will flow from solvent to solution. Okay. So now let us see. Suppose I have a two columns here, two tubes. So suppose you have a system like this. So it's connected like this. So here it is your solution, and here it is your solvent. So solution, solvent. Okay. So what happens? So the solvent molecules will also be here. This, of course, the solution is also made up of the solvent molecules only, right? And it will be there here also. Okay. But at the start of the experiment, suppose I am starting this experiment, what will happen is both of them will have equal here. So both of them will have been raised to the same level. Okay. Now because of osmosis, what will happen is, because there is a flow of solvent molecules from pure solvent into the solution, what will happen is the solvent level will decrease here and increase here, right? It will increase to a new level and decrease here. Okay. So this will keep on happening because solid molecules, the level of the solvent here in the tube rises here. Now it will rise till an equilibrium is reached. So an equilibrium is reached. Level of solution in the tube does not rise further. So what happens is, at this stage, the excessive hydrostatic pressure created on the solution side exactly balances the tendency of the solvent molecules to pass through the membrane. See, this flow will continue till an equilibrium reach. At the equilibrium stage, what happens is, because there is a higher level of solution here than here, this will put extra pressure on the solution side, and this pressure will stop the inflow of the solvent molecules through this semi-permeable membrane. So at this stage, we say that hydro in equilibrium is reached. Now, alternatively, if you have to stop the flow of solvent molecules, okay. Now, this, suppose I say that it has created extra pressure pi, right? Once the flow of solution has risen in this tube, it has created an extra pressure pi. Now, what I can tell is, alternatively, I'll define that pi as a new pressure called as osmotic pressure. Pi is the pressure that must be applied to the solution to stop the influx of the solvent. Okay. So this osmotic pressure, OP, I'll let me write pi, has been found to depend only on concentration of the solution. It's a colligative property, meaning that it does not depend on the nature of the particles but only on their number. It has been found experimentally that this relation holds good, that is pi b is equal to into RT. So where pi is the osmotic pressure, V is the volume of solution in liters, containing N2 moles of solute. Okay, see 2 here represents solute and 1 is for solvent. Of course, there is no mention of 1 here. So just in case wherever it is mentioned, then it means N is for solute. R is the gas constant, T is the temperature at temperature, working temperature. Now, we use a new page. Now pi V, since is N2 RT, what is your N2? N2 is weight of the solute divided by its molar mass of the solute, RT. Now if this is known, this is known, this is known, this is known and this is known, so your molar mass of the solute can be calculated R into T divided by pi V. Okay, so this osmotic pressure is another method for determining the molar mass of the solutes. So this is widely used for determining the molar masses of like proteins, polymers and macromolecules. And also the osmotic pressure method of determining the molar mass of solutes has advantage over other methods, as pressure measurement is around room temperature. So this is around room temperature and molarity is used instead of molality. Advantages: one is room temperature, second molarity is used instead of molality. Okay. So as compared to other colligative properties, its magnitude is large even for very dilute solutions. So this technique of osmotic pressure for determination of molar mass of solute is particularly useful for biomolecules, as these biomolecules are not stable at higher temperatures. Since a room temperature is used, this is advantageous. So biomolecules are not generally stable at higher temperatures, and of course polymers have poor solubility. So that is why this is very advantageous. Now your pi V is equal to N2 RT. If I bring V, it is N2 by V by RT is equal to pi. So this one is concentration of solute, right, into RT. So this relation is called as Van 't Hoff's equation. Okay, where now if I put this is the concentration of solute, or in other terms I could have represented as 2. So pi is equal to RT. See here, this term is somehow is exactly identical to that of your PV is equal to nRT, ideal gas equation, except that here instead of P, pi has been replaced in this Van 't Hoff's in this relation. Now this striking resemblance suggests that solute molecules are dispersed in a solvent the way gas molecules are dispersed in the empty space. Thus the solute is analogous to the gas molecules, and the solvent is analogous to the empty space between the gas molecules. Now regarding in osmosis, we talk about three terms, which is isotonic, hypertonic, and hypotonic. So let me take an example of cell. A cell is kept in a solution. In an isotonic solution, if it is kept, so two solutions have the same osmotic pressure. At a given temperature. So it means the cell is there. There's some of the water. Suppose this is your water solvent. So H2O flows out of the H2O flows in, and there is no relative change in the volume of the cell. Whereas in hypertonic solution, if a cell is placed in hypertonic, solution, there will be net flow water out of the cell, and what will happen? Cell will lose water, lose volume, correct? So there is a net flow of water, and this water keeps flowing out, and this will lose volume. In a hypotonic solution, there will be net flow of water into the cell in the will gain volume. Water flows inside, water flows inside in an, so this is your, so that was about three terms: isotonic, hypertonic, hypertonic. Okay. So osmosis, osmotic pressure, Van Top's equation, and your three terms. So thank you so much